There is a useful way to think about the beginning of deep space. It does not begin at a single dramatic border. There is no place where Earth suddenly ends and the universe begins. Instead, the protections around you thin away in layers, and each layer changes the conditions that a human body or a spacecraft must endure. At the surface, you live beneath an atmosphere that absorbs and scatters. Radiation slows small incoming objects, carries heat, and provides the pressure your body expects. Beneath that atmosphere, you are also surrounded by Earth's magnetic environment, shaped by motions deep inside the planet and stretched far into space by its interaction with the solar wind. These protections are so constant that they are easy to forget. Even astronauts aboard the International Space Station have not left all of them behind. The station circles Earth at roughly 400 kilometers above the surface, well inside the region dominated by our planet's magnetic field. Its crew experiences a radiation environment far harsher than the one at sea level, but their location still matters. Earth's magnetic field reduces exposure to some energetic particles, while the planet itself blocks part of the sky at any given moment. So the familiar photographs from low Earth orbit can be a little misleading. An astronaut floating beside a window appears to be surrounded by open space. Below, Earth curves away in blue and white. Above, the sky is black. The station completes an orbit in about 90 minutes, moving fast enough that sunrise and sunset can return again and again during a single day. Visually, it seems as though Earth has already been left behind. Physically, it has not. The station remains close enough to the planet that crews can communicate with mission control with very little propagation delay. Cargo vehicles can still reach them. A docked spacecraft can provide a path home. And around the station lies a magnetic environment that is connected to the same planetary field you can measure with a compass on the ground. Farther out are the Van Allen radiation belts, regions where energetic charged particles become trapped by Earth's magnetic field. They are not solid shells, and they are not fixed in shape or intensity. They respond to solar activity, sometimes changing substantially as conditions around Earth change. To travel toward the Moon, a spacecraft must pass through this broader magnetic landscape and eventually spend long periods beyond the strongest protection available in low Earth orbit. That is the first real change in our journey. Not danger arriving all at once, but protection becoming less complete. The farther you move from Earth, the less useful it becomes to imagine space as one uniform emptiness. Near Earth, magnetic fields, trapped particles, the upper atmosphere, and the planet itself all shape the environment. Beyond Earth, another set of conditions begins to take over. Radiation comes from the sun and from far beyond the solar system. Communication takes longer. Returning home requires more time. Every system aboard the spacecraft carries more responsibility because the world that built it is becoming harder to reach. And yet, from only a few hundred kilometers above the surface, none of this is obvious. Earth still fills the windows. The lights of cities still pass beneath the night side. Cloud systems still turn over oceans. The planet remains close enough to feel less like a distant world than a vast surface moving below you. This is where we will begin, not at the edge of the solar system, but inside the last layers of a home that extends farther into space than the ground beneath your feet. To move beyond low Earth orbit is to discover that Earth does not end at the atmosphere. Its influence continues outward through space in forms you cannot see directly. Magnetic fields, charged particles, plasma, and radiation create a layered environment around the planet. A spacecraft crossing those layers is not simply moving farther from the ground. It is moving from one physical regime into another. Near Earth, the magnetic field is shaped by motions deep inside the planet. Far below the crust and mantle, liquid iron circulates through the outer core. Earth's rotation helps organize those motions, and together they sustain a planetary dynamo. The result is a magnetic field whose influence reaches far beyond the atmosphere. If the solar wind did not exist, the field would spread outward in a more balanced way. But the sun is constantly sending streams of charged particles through the solar system. When that solar wind reaches Earth, it pushes against the magnetic field and reshapes it. On the side facing the sun, the field is compressed. On the night side, it is drawn outward into a long magnetotail. The entire structure changes as solar conditions change. A stronger solar wind can press the sunward boundary closer to Earth. Disturbances arriving from the sun can reorganize the field, accelerate particles, and produce geomagnetic storms. What surrounds the planet is not a rigid shell. It is a responsive system, and within that system are the Van Allen belts. These regions contain energetic particles held by Earth's magnetic field. Many spiral back and forth along magnetic field lines, while also drifting around the planet, creating broad zones where radiation levels can be much higher than those encountered below. The belts were revealed at the beginning of the space age when instruments aboard Explorer 1 detected unexpectedly intense radiation around Earth. Their discovery changed the way early spacecraft missions were planned. A vehicle traveling toward the moon would need to cross these regions, but crossing them was not the same as remaining inside them. Exposure depended on trajectory, duration, solar conditions, and the shielding provided by the spacecraft. During the Apollo missions, crews passed through the radiation belts relatively quickly. Beyond them, the environment changed again. The spacecraft was now traveling through cislunar space, the enormous region between Earth and the Moon, where the protective influence experienced in low Earth orbit was reduced, and where energetic particles from the Sun and the galaxy became more important. This was unfamiliar territory for the human body for nearly all of human history. Every person who ever lived remained beneath the atmosphere and within Earth's magnetic environment. Then, for several brief journeys between 1968 and 1972, humans traveled far enough outward to experience space beyond low Earth orbit directly. One of the strangest reports from those missions came when the cabin lights were dimmed. Some astronauts noticed brief flashes. They appeared even when the astronauts closed their eyes. Sometimes the flashes looked like small points. Sometimes they resembled streaks or short lines moving across the visual field. They were not light entering through a window. Energetic particles were passing through the spacecraft and interacting with the astronauts themselves. A charged particle traveling at high speed could cross the hull, continue through tissue, and produce a visual sensation through interactions involving the eye or nervous system. Later Apollo experiments studied the phenomenon more carefully and strengthened the connection with these flashes and high-energy cosmic particles. For the astronauts, there was little to do when one appeared. A flash would arrive, vanish, and perhaps another would come later. The experience revealed something difficult to understand from the ground. Radiation in deep space is often invisible right up until it interacts with matter. There is no glowing cloud approaching the spacecraft, no visible wave moving across the cabin. High-energy particles can pass through structures and through living tissue without announcing themselves in advance. Most pass without producing anything the senses can notice. The flashes were unusual because, for a moment, the radiation environment became perceptible. Outside Earth's stronger protection, two broad sources of energetic particles matter greatly to human exploration. One comes from the Sun. Solar eruptions can accelerate protons and other ions to high energies. Some events produce large increases in radiation across interplanetary space. Their intensity can vary greatly, and a crew far from Earth would need warning systems, shielding strategies, and places inside the spacecraft where additional mass could be placed between people and incoming particles. The other source comes from beyond the solar system. Galactic cosmic rays arrive from many directions. They include atomic nuclei accelerated to high energies by processes elsewhere in the galaxy. Unlike a temporary solar particle event, this background does not simply disappear when the sun becomes calm. The challenge is different. Solar particle events can sometimes become intense over relatively short periods. Galactic cosmic rays create a more persistent exposure that accumulates during long journeys. Shielding against both is complicated. Adding material can reduce many forms of radiation, but spacecraft cannot carry unlimited mass. And some of the highest energy particles can penetrate substantial shielding, occasionally producing secondary particles when they strike the spacecraft itself. So deep space radiation protection becomes an exercise in reduction rather than complete isolation. Mission planners can choose materials carefully. They can place water, supplies, equipment, and other useful mass around selected areas of a vehicle. Crews can retreat to more protected locations during elevated solar activity. Mission duration can be considered when estimating cumulative exposure. But nothing carried aboard a spacecraft reproduces the environment of Earth. That distinction becomes clearer as the Moon approaches. From Earth, the Moon seems close enough to belong almost to the same neighborhood. Light crosses the average distance between Earth and the Moon in a little more than a second. Apollo crews needed only a few days to travel between them. And from the lunar surface, Earth remains plainly visible, suspended above the horizon, for many locations, as a bright, colorful world. Yet physically, the Moon is already a very different place. It has no dense atmosphere surrounding its surface. It does not possess a global magnetic field comparable to Earth's. A person outside a habitat there depends on layers of engineered protection for pressure, oxygen, temperature control, micrometeoroid protection, and radiation reduction. The difference between Earth and the Moon is therefore not simply a difference in scenery. It is a change in what the environment provides without being asked. On Earth, air surrounds you automatically. Pressure surrounds you automatically. A large part of the radiation's protection supplied by the atmosphere and magnetic environment is present whether you think about it or not. On the Moon, these conditions must be manufactured. Every breath belongs to a system. Every comfortable temperature depends on machinery. Every sealed volume becomes a small artificial extension of the world left behind. And still, Earth is close. A radio signal can cross the distance in a little over a second. A journey home can be measured in days. The planet remains visible as a world rather than merely a point of need. This makes the Moon a useful threshold in our outward journey. It is far enough away to reveal how much of human survival depends on Earth's environment, yet close enough that Earth still dominates the practical logic of the mission. The deeper changes have not happened yet. Sunlight remains strong. Communication remains relatively fast. The distance home, although serious, can still be crossed on the scale of a few days. The Moon is not the point where Earth disappears. It is the place where you begin to understand what Earth had been doing for you all along. Beyond the Moon, distance begins to change more than the view. For the first time, the speed of light becomes something you can feel in the structure of a mission. A radio signal, leaving Earth, still travels as fast as anything in nature can travel. It crosses empty space at nearly 300,000 kilometers each second. On Earth, that speed seems instantaneous. Around the Moon, it creates only a brief pause. But once a spacecraft begins traveling toward Mars, even light requires patience. Earth and Mars are constantly moving around the Sun, so the distance between them changes enormously. At favorable times, the two worlds are separated by tens of millions of kilometers. At other times, they can be more than 400 million kilometers apart. A signal traveling between them may need only a few minutes, or it may need more than 20, and that is one way. This creates a boundary unlike the magnetic ones we left behind earlier. Nothing physical surrounds it. There is no radiation belt to cross, and no instrument that suddenly announces the transition. Instead, conversation gradually stops behaving like conversation. Imagine asking someone on Earth a simple technical question from Mars. You speak, then you wait. The message travels across interplanetary space, while both planets continue moving in their separate orbits. Eventually, it reaches a receiving station on Earth. Someone listens, examines the problem, considers an answer, and transmits a response. Then the response begins the same journey back. By the time you hear it, the situation that produced the question may already have changed. This is why robotic explorers on Mars cannot depend on people on Earth for every movement. A rover encountering rocks, slopes, or other terrain cannot simply pause before every wheel rotation and wait for a human operator to tell it what to do. The delay is too long. Instead, commands are planned ahead, and increasingly capable onboard software helps spacecraft interpret their surroundings and carry out parts of their work independently. For a machine, this is an engineering requirement. For a human crew, it would become a different way of living. Mission control could still provide expertise. Doctors could still review medical data. Engineers could still study a malfunction and send detailed instructions. But Earth could no longer participate in the first moments of an emergency. Those moments would belong entirely to the crew. A pressure warning appears, a valve fails, a spacesuit begins losing pressure during work outside the habitat. Someone becomes seriously ill. The people on Mars cannot hand the situation back to mission control. They must act first. Earth can advise later. This separation would influence nearly every part of a human mission to Mars. Crew members would need broader medical skills than astronauts working close to Earth. They would need enough engineering knowledge to diagnose systems without immediate outside guidance. Spacecraft and habitats would need greater autonomy, deeper reserves, carefully chosen spare parts, and procedures designed for situations in which expert advice may arrive only after the most important decisions have already been made. The crew would still be connected to Earth, but connection would no longer mean immediacy. And there are periods when even that delayed connection becomes more difficult. As Earth and Mars move around the Sun occasionally lies near the line of sight between them. During this geometry known as solar conjunction, radio communication can be degraded because signals passing close to the Sun encounter ionized material in the solar environment. Robotic Mars missions are prepared for these intervals. Engineers reduce the number of complex commands sent during the most difficult part of conjunction. Spacecraft continue performing limited activities independently until reliable communication improves again. For people living on Mars, the principle would be similar. The planet would have to become more self-contained for a time. This is an important step outward because it changes the meaning of home. At the International Space Station, Earth is physically close and visually overwhelming. From the Moon, Earth is smaller, but still appears as a recognizable world. From Mars, Earth becomes something much more delicate. It appears as a point of light. Under favorable conditions, you could see it in the Martian sky, but you would not see continents. You would not see oceans or clouds with your unaided eyes. The entire human world would be reduced to reflected sunlight arriving from a distant planet. Every language being spoken at that moment would be there. Every city, every forest, every person waiting for a message from the crew. All of it would occupy a point too small for your eyes to resolve. There is a long history of humans using distant lights to orient themselves. Sailors once watched stars rise above horizons to determine direction. Travelers learned the seasonal positions of bright objects. Generations looked upward and recognized familiar patterns that connected one place to another. A crew on Mars might experience something almost inverted. Instead of using a star to find home, they could look toward a star-like point and know that home itself was there. The physical distance would remain unchanged by that knowledge. But the relationship might feel different. Mars also introduces another separation. You cannot simply leave whenever you choose. Space travel between planets depends strongly on orbital geometry. Earth and Mars move at different speeds around the Sun, and efficient trajectories are available during recurring launch opportunities rather than continuously. A crew arriving at Mars therefore enters a schedule partly dictated by celestial mechanics. The planets decide when travel is practical. If equipment fails shortly after arrival, returning immediately may not be a realistic option. If someone becomes homesick, there is no early flight. If a medical problem develops, the answer cannot automatically be evacuation. For much of the mission, the crew must continue, because orbital mechanics has removed the possibility of a quick retreat. This is very different from isolation on Earth. Remote research stations can be difficult to reach. Submarines may remain submerged for long periods. Ships can spend weeks far from land, but all of them exist inside the same planet system of support. The same atmosphere surrounds them. The same hospitals, factories, transportation networks, and emergency services exist somewhere beyond the horizon. Mars does not share that infrastructure. Almost everything required for survival must already be present. Air must be managed, water must be recovered and reused, food must be stored, produced, or some combination of both. Carbon dioxide must be removed from the habitat. Waste must be processed. Power must continue. Temperature must remain within tolerable limits. And small failures must be prevented from becoming large ones. This changes the value of ordinary objects. A filter is no longer merely a filter if another one cannot arrive for many months. A pump is not simply a machine if it belongs to the system circulating water through the habitat. A damaged connector, worn seal, or failed sensor may deserve hours of attention because there is no nearby warehouse holding replacements. The farther you move from Earth, the more every kilogram carried with you becomes part of a closed inventory. That fact changes how engineers think about reliability. On Earth, redundancy often means having another machine available. In deep space, redundancy may mean carrying another machine through millions of kilometers of travel. Mass costs energy. Every spare part competes with food, water, scientific instruments, shielding, fuel, and other equipment for space aboard the mission. So designers cannot simply carry several copies of everything. Some systems must be repairable, some components must serve more than one purpose, and eventually, crews may need the ability to manufacture certain replacement parts from materials already available to them. Mars is close enough that these problems can still be imagined in familiar terms. Supplies can be sent there. Robotic missions already demonstrate that carefully planned spacecraft can reach the planet. Future cargo could be launched before a crew and placed where it will be needed. But compared with the Moon, the rhythm of support has changed completely. A missed delivery cannot simply be replaced the following week. A failed launch may alter plans for months or years. The mission has become less like an expedition near home and more like a temporary branch of civilization, operating at another planet. Even sunlight begins to reflect that distance. Mars receives much less solar energy than Earth because it orbits farther from the Sun. The Sun still dominates the daytime sky. Solar panels, can still provide substantial power. The star still feels central to the environment, but its energy is reduced enough that power systems must account for weaker illumination, seasonal changes, dust in the atmosphere, and the accumulation of dust on exposed surfaces. Nothing has disappeared completely. That is what makes Mars such an instructive threshold. Earth is still visible, the sun is still strong, radio still works, supply missions remain possible, return remains possible. Yet, every one of those connections has become thinner. A few hundred kilometers above Earth, the planet could respond almost immediately. At lunar distance, it could still speak with only a slight delay. At Mars, the response arrives from an earlier moment. And for the first time on our journey outward, the people traveling through space would have to begin living as though Earth were not the place where every immediate solution comes from. They would carry part of Earth with them instead. Inside tanks, inside computers, inside medical kits and repair lockers, inside procedures learned before departure, and inside the accumulated knowledge of a world that is now too far away to answer in time. Beyond Mars, the solar system begins to change in a way that can be measured with something as simple as light. The sun is still there. It is still the gravitational center of everything moving around it, but its energy is spreading across an ever-growing sphere, and with distance, each square meter receives less of what left the solar surface. The relationship follows the inverse square law. Move twice as far from the sun, and the same light is spread across 4 times the area. Move 3 times as far, and the intensity falls to 1/9. The decline is not a steady subtraction. It accelerates with distance. Near Earth, sunlight is abundant enough that spacecraft can collect useful amounts of power with relatively modest solar arrays. At Mars, sunlight is weaker, but still practical. Farther out, the calculation begins to change. A spacecraft crossing the asteroid belt can still use solar power, but larger collecting areas become useful. More surface must be exposed to the sun. More structure is required to support the arrays. More mass must be carried through launch and every maneuver that follows. This is one of the ways distance quietly enters spacecraft design. A photon does not become weaker during its journey. There are simply fewer of them arriving through the same area. And by the time a spacecraft reaches the neighborhood of Jupiter, sunlight has fallen to only a few % of the intensity Earth receives. The sun remains visually brilliant. Looking directly toward it would still be damaging to the eyes. But the amount of energy falling across a surface is dramatically reduced. These are 2 different ideas that human experience tends to combine. Brightness is something your eyes perceive. Power is something a machine must collect. At Jupiter, the sun can still look unmistakably like the sun, while providing far less usable energy than it does near Earth. For much of the history of outer solar system exploration, this was one reason spacecraft traveled with their own long-lived power sources. Voyager 1 and Voyager 2 carried radioisotope thermoelectric generators. So did Galileo when it entered orbit around Jupiter. Cassini used the same general approach on its long journey to Saturn. New Horizons carried one as it traveled toward Pluto and the Kuiper Belt. These devices do not operate like nuclear reactors. They have no controlled chain reaction. Instead, they use heat produced naturally as a radioactive material decays. That heat creates a temperature difference across thermoelectric materials, producing electrical power. The process is steady. It does not depend on whether a spacecraft is pointed toward the sun. It does not depend on daytime or nighttime. And most importantly, for our journey outward, it does not become weaker simply because the spacecraft has crossed another billion kilometers of space. The available power does decline gradually as the radioactive material decays and the generating system ages, but the sun no longer determines whether the spacecraft can remain awake This creates another quiet threshold. Closer to Earth, a spacecraft can live largely on energy that arrives from the star. Farther away, it may need to carry an energy source from home. Juno demonstrated that the boundary is not absolute. When it traveled to Jupiter, it became the first solar-powered spacecraft designed to operate there. Its 3 long solar wings were built to collect enough light from a sun more than 5 times farther away than it appears from Earth. The arrays are large because they have to be. There is no dramatic moment when solar power stops working. Instead, engineering becomes progressively more demanding. A mission designer can compensate for weaker sunlight by increasing panel area, improving cell efficiency, reducing spacecraft power consumption, or accepting narrower operating margins. Eventually, however, every additional square meter has consequences. Solar panels have mass. They require structural support. They must survive launch vibration. They must deploy correctly after years in space. They can accumulate radiation damage. They introduce larger surfaces that must be controlled as the spacecraft turns. And every watt they produce must be distributed carefully among communications, computers, instruments, heaters, navigation systems, and the equipment keeping the vehicle alive. At these distances, heat becomes part of the same calculation. Space itself does not become colder because you have traveled farther from Earth. Vacuum does not behave like winter air. There are too few particles to carry heat away through ordinary conduction or convection. A spacecraft loses much of its heat by radiation. It gains heat from sunlight, from electronics, from power systems, and sometimes from nearby planets or moons. Moving away from the sun changes that balance. Less solar energy reaches exterior surfaces. Shaded components can become extremely cold. Lubricants, batteries, instruments, propellant lines, and electronics may each have a preferred temperature range, and spacecraft designers must keep those parts within it. Sometimes that requires heaters, and heaters require electricity, so reduced sunlight affects the mission twice. There is less incoming energy to collect, and more of the available electrical power may have to be spent. Keep it critical hardware warm enough to function. This is one reason the outer solar system is such a demanding environment for machines. Not because everything freezes instantly, it does not. A spacecraft carries its own heat. Computers generate warmth. Power sources generate warmth. Insulation slows the rate at which that energy escapes. The challenge is controlling where the heat goes. One component may need protection from becoming too cold, while another must be prevented from becoming too warm. Sunlit and shaded surfaces can experience very different conditions. Thermal control becomes a continuous balancing act, performed across structures that cannot be repaired by a technician standing nearby. And Jupiter adds something that distance alone could never predict. It has a magnetic environment of its own. Jupiter's magnetic field extends enormously into surrounding space and traps populations of energetic, charged particles. Close to the planet, these radiation belts can create conditions severe enough to damage spacecraft, electronics, and instruments. So, a vehicle reaching Jupiter does not simply encounter weaker sunlight. It enters another magnetic world. The comparison with Earth is revealing. Near Earth, the planetary magnetic field helps shape a protected environment in which human spaceflight has largely taken place. Near Jupiter, the magnetic field creates intense trapped particle regions that spacecraft must be designed to endure. The same basic physics can therefore have very different consequences depending on the planet. Magnetic fields guide charged particles, but what matters for a spacecraft is which particles are present, how energetic they are, and where the field concentrates them. Juno was designed with this in mind. Many of its sensitive electronics were placed inside a heavily shielded enclosure. Its orbit was chosen so that the spacecraft could repeatedly pass close to Jupiter while limiting the time spent in some of the harshest radiation regions. The path is highly elongated. Juno moves inward, gathers observations during close approaches, and then travels much farther from the planet before returning again. The orbit itself becomes part of the protection. This is a pattern that appears repeatedly in deep space exploration. Safety does not always come from building a thicker wall. Sometimes it comes from choosing where to go, sometimes from choosing how long to remain there, sometimes from orienting the spacecraft so one side absorbs the greater burden, sometimes from switching instruments off, sometimes from allowing a machine to wait. Distance encourages a different kind of patience. At Jupiter, communication with Earth no longer resembles the almost immediate exchange familiar in low Earth orbit. Radio waves still travel at the speed of light, but even light needs many tens of minutes to cross the changing distance between Jupiter and Earth. A spacecraft cannot report a problem and receive an immediate instruction. By the time engineers learn that something has happened, the event is already part of the past. They can examine telemetry. They can reconstruct what the spacecraft experienced. They can design a response. But during the interval between the problem and the arrival of that response, the spacecraft must protect itself. This is why deep space vehicles carry autonomous fault protection systems. If a computer detects conditions outside safe limits, it may shut down non-critical equipment, place instruments into protected states, orient the spacecraft toward the Sun or Earth, and wait for instructions. The machine must know how to become less active when uncertain. There is an appealing simplicity in that principle. When something goes wrong far from home, the first response is often not to do more. It is to preserve what is working, maintain power, maintain temperature, maintain communication. Avoid making the situation worse. Then wait for distant human beings to understand what happened. For robotic missions, that delay can be designed into the system. For people, it would change the meaning of assistance. Imagine a future crew moving through the region of Jupiter. The signal they send toward Earth crosses hundreds of millions of kilometers before anyone receives it. Mission control can still help. Specialists can still think through complex problems. But the crew lives in the present while Earth responds to the past. The farther the vehicle travels, the larger that gap becomes, and there is another gap widening at the same time. Resupply. Near Earth, spacecraft operate within a transportation system. Vehicles can launch cargo, crews can return. Replacement equipment can be delivered. Even when those operations are difficult and expensive, they are conceivable on human timescales. Mars stretches that system. Jupiter breaks it. A conventional journey from Earth to Jupiter is measured in years rather than days or months, depending on trajectory and propulsion. A replacement component cannot be dispatched after a failure with any expectation that it will arrive soon enough to solve an urgent problem. Everything important must already be aboard. That includes hardware, it includes medical capability, it includes knowledge, it includes the ability to improvise. A distant crew would need to think of the spacecraft less as a vehicle and more as a small, closed world. The distinction matters. A vehicle takes you somewhere. A world must keep you alive while you are there. Air moves through machines. Water circulates through machines. Heat travels through carefully designed paths. Electrical power flows from a limited source. Waste becomes material that may need to be recovered or processed. Broken objects become reservoirs of parts. Nothing is casually disposable when the nearest industrial civilization is hundreds of millions of kilometers away. And still, at Jupiter, you remain unmistakably inside the Sun's domain. Its gravity governs the planets. Its light reaches the spacecraft. Its wind moves through the region. The Sun is diminished, but it has not withdrawn. From here, the journey outward continues into distances, where even those remaining connections begin to change. Saturn waits much farther on, beyond Saturn, Uranus, beyond Uranus, Neptune. And with each orbit crossed, sunlight spreads thinner across the expanding dark. Past Jupiter, the sun begins to lose something more subtle than brightness. It still rules the architecture of the solar system. Saturn, Uranus, and Neptune remain bound to it, circling along paths set by gravity. But the energy arriving from the sun has become so diluted that a spacecraft can no longer treat sunlight as an abundant background resource. At Saturn, nearly 10 times farther from the sun than Earth is, only a little more than 1% of Earth's solar intensity remains. That sounds darker than it would look. Human eyes are remarkably adaptable. If you could stand somewhere with a clear view of the sun at Saturn's distance, the sun would still be painfully bright to look at directly. It would appear smaller, but unmistakable. The surrounding world would not disappear into blackness. The important difference is not whether your eyes could see. It is how much energy is arriving. A square meter of surface near Earth receives far more solar power than the same square meter near Saturn. For a machine, that difference changes everything. Solar arrays must become larger, power budgets more constrained, and thermal systems more deliberate. Cassini did not depend on sunlight for its electrical power while it spent years studying Saturn. It carried radioisotope, thermoelectric generators, allowing heat from radioactive decay to supply electricity far from the inner solar system. The spacecraft, therefore, brought part of its energy environment with it. That choice helped Cassini remain active through repeated passages around Saturn, long eclipses, changing orientations, and years of operations at a distance where sunlight could no longer be treated casually. In January of 2005, Cassini released the Huygens probe toward Titan. Huygens carried batteries for its brief independent mission. After entering Titan's thick atmosphere, it descended beneath layers of haze and eventually reached the surface. The images it returned showed rounded pieces of water ice and a landscape shaped by processes involving liquid hydrocarbons. The scene was illuminated by sunlight that had already crossed roughly 1.5 billion kilometers from the sun before filtering through Titan's atmosphere. The light was enough for cameras. It was enough to reveal a world. But the sun that created noon on Earth had become a much more distant source of energy. And beyond Saturn, the separation grows rapidly. Uranus orbits at a mean distance of a little more than 19 astronomical units. By the inverse square law, sunlight there is only about 1/370th of the intensity received at Earth. Again, darkness is not quite the right image. The sun is still the brightest object in the sky. But the connection between sunlight and warmth has weakened almost beyond ordinary experience. A spacecraft near Uranus must pay close attention to the heat produced inside itself. Electronics, radioisotope power systems, heaters, and insulated compartments create local pockets of usable temperature inside a surrounding environment where direct solar heating is small. Thermal engineering becomes less about escaping the sun and more about keeping precious internal heat where it is needed. This reversal is easy to miss. Near Earth, spacecraft frequently need to reject heat. Electronics generate it. Sunlit surfaces absorb it. Radiators must carry it away. In the outer solar system, waste heat can become valuable. A watt that leaves a computer as heat may help keep another component within its operating range. A heater that seems minor near Earth can become part of the survival logic of an instrument farther out. Energy is counted twice. First as electricity, then as warmth. Voyager 2 reached Uranus in January of 1986. No spacecraft has returned for another close visit since. The encounter was brief because Voyager was not entering orbit. It was passing through, using a carefully planned trajectory that carried it past the planet and onward toward Neptune. By then, the radio link to Earth already revealed what distance had done. Light from the Sun needs about 2 hours and 40 minutes to reach Uranus at its mean distance. A radio signal crossing a comparable span cannot do any better. So the spacecraft could not be flown like a remote-controlled vehicle. The commands guiding the encounter had to exist before the observations happened. Camera pointing, instrument sequences, data handling, spacecraft orientation. Each action had been designed by people on Earth and stored aboard a machine that would execute those instructions, while its creators remained billions of kilometers away. The scientists would learn how well the plan had worked only after the results traveled home. There is a strange temporal separation in that arrangement. The spacecraft experiences the event first. Earth learns about it later. The deeper into the outer solar system a probe travels, the more mission control becomes an observer of history. By the time a signal arrives, the moment that produced it is gone. The machine has already moved on. At Neptune, this delay stretches farther. Neptune circles the Sun at about 30 astronomical units. Sunlight there has fallen to roughly 1/900th of the intensity at Earth. The Sun still shines, but it now takes a little more than 4 hours for that light to cross the average distance from the Sun to Neptune. Voyager 2 arrived there in August of 1989, becoming the first and still the only spacecraft to visit Neptune closely. The encounter had to be prepared with the same discipline used at Uranus, but with even greater separation from Earth. Voyager passed only a few thousand kilometers above Neptune's cloud top. It studied the planet's atmosphere, rings, magnetic environment, and moons before sweeping onward toward Triton. The images that came back showed a dynamic blue planet, bright clouds, and large atmospheric structures moving through a world, receiving only a tiny fraction of the sunlight familiar on Earth. Yet none of those images reached mission controllers at the moment they were taken. The photographs began as patterns of electrical charge inside a camera. They became digital information. That information traveled through the spacecraft, was encoded into a radio transmission, crossed billions of kilometers, and finally arrived at antennas on Earth hours later. Only then could a human being see what Voyager had already passed. That delay changes the nature of exploration. Close to home, we often imagine exploration as seeing and responding. You notice something. You change course. You point an instrument. You ask another question. At Neptune, those steps become separated by hours. A new observation cannot immediately produce a new command. The spacecraft must carry enough foresight to continue without waiting. This is one of the less visible achievements of the Voyager missions. Their cameras and detectors are famous because they showed us worlds no one had seen closely before. But the missions also demonstrated something about autonomy. A deep space probe has to survive intervals in which Earth knows less about its present condition than the spacecraft itself. If a fault develops, onboard systems must recognize at least some kinds of trouble and protect the vehicle long before engineers can respond. Power has to remain stable. Attitude control has to preserve communication. Temperatures have to remain within limits. The antenna eventually has to point toward a planet that is now only a bright star from the spacecraft's perspective. And the spacecraft has to wait. Not emotionally, of course, but functionally. It waits for radio waves to cross the solar system. There is an older human experience that makes this distance easier to imagine. For most of history, people who left home on long voyages also left immediate communication behind. A ship crossing an ocean could disappear beyond the horizon and remain unheard from for weeks or months. Families continued their lives without knowing the exact position of the travelers. Messages moved only as fast as another ship could carry them. Deep space communication has something of that old rhythm, but with one important difference. There is no weather to blame for the delay. No faster vessel can overtake the message. The limit is built into space-time. Even a perfect transmitter, sending a perfect signal through completely empty space, must wait for light to make the crossing. At Neptune, this means the solar system has become large enough for different places within it to possess a noticeably different presence. Earth has its present, the spacecraft has another. Radio connects them only by carrying records from one present into the future of the other. And beyond Neptune, even the planets begin to thin away. The Kuiper Belt extends through a broad region populated by icy bodies left from the formation of the solar system. Pluto travels there, so do many smaller worlds. New Horizons crossed this region after its Pluto encounter in 2015, sending its observations back through a radio link so faint that returning. The complete flyby dataset required many months. The difficulty was not that the data had farther to travel in the ordinary sense of slowing down. Every bit still moved at light speed. The difficulty was that radio energy spreads with distance just as sunlight does. By the time a spacecraft signal reaches Earth from billions of kilometers away, very little of the transmitted energy is intercepted by a receiving antenna. So the data rate must remain modest enough for the signal to be distinguished reliably from noise. A picture can cross the solar system. It may simply arrive piece by piece. This is another form of subtraction caused by distance. First conversation becomes delayed, then rapid data becomes difficult, then immediate intervention becomes impossible. But one connection still remains. Even beyond Neptune, the spacecraft is traveling through material flowing outward from the sun. The solar wind has become thin, but it has not ended. The sun's magnetic influence is still carried through that moving plasma. The outer planets may be behind us now, and sunlight may have become a minor contributor to the spacecraft's power. But the vehicle has not yet entered interstellar space. There is still a larger boundary ahead. It lies far beyond Neptune, beyond most of the familiar planetary map, where the outward flow from the sun finally meets the material between the stars. For all the distance already crossed, the spacecraft is still inside the sun's breath. Beyond Neptune, the solar system begins to feel less like a collection of worlds and more like a structure made of distance. The familiar planets are behind you now. The sun still holds them all through gravity, but most of the objects ahead are small, cold, and separated from one another by enormous stretches of space. Pluto is one member of this outer population. Around and beyond its orbit are many other icy bodies, remnants of the material from which the planets formed. This region is usually called the Kuiper Belt. It is not a narrow ring and not a crowded field of debris. A spacecraft could cross it for years without coming close to anything large enough to see with the unaided eye. Distance dominates everything, even here. However, the sun is still doing more than shining. It is sending matter outward. The solar wind begins high in the sun's atmosphere, where plasma becomes hot enough to escape the star's gravity. Protons, electrons, and other charged particles stream away in every direction, carrying magnetic fields with them as they move across the solar system. Near Earth, this wind is familiar because it shapes our magnetosphere. Far beyond the planets, the same flow continues. It has become thinner with distance, but it has not disappeared. The sun is therefore surrounded by something much larger than its visible light. It creates a vast region in which solar particles and solar magnetic influence dominate the local environment. That region is called the heliosphere. You can imagine it not as a hard bubble, but as a zone of influence inflated by a continuous outward flow. Inside, the solar wind pushes away from the sun. Outside, the local interstellar medium presses inward. The boundary between them is created by pressure, motion, magnetic fields, and plasma interacting across scales far larger than the planetary system. Most people picture when they hear the word solar system. For a long time, astronomers could model this region only indirectly. They could measure the solar wind near Earth. They could study how cosmic rays changed with solar activity. They could observe neutral atoms and other signals that carried information from distant parts of the heliosphere. But no spacecraft had crossed its outer layers. Then, the Voyagers continued going. Voyager 1 and Voyager 2 were launched in 1977 for encounters with the giant planets. Their original work was planetary. They photographed Jupiter and Saturn. Voyager 2 continued to Uranus and Neptune. Their cameras transformed distant points in telescopes into landscapes, atmospheres, rings, clouds, moons, and weather. But after the planetary encounters ended, the spacecraft did not stop. There was nothing to stop them. Their trajectories carried them outward on paths that would never return to the planets. The mission changed. The same machines that had been built to visit worlds became probes of the outer heliosphere. Decades passed. The sun grew smaller behind them. Radio signals took longer to arrive. The electrical power available from their radioisotope generators gradually declined, and still their instruments continued measuring the space around them. Eventually, the environment began to change. The solar wind had spent tens of billions of kilometers expanding outward. By the time it reached the far reaches of the heliosphere, it was confronting the material that exists between stars. That interstellar material is sparse by any terrestrial standard. But space does not have to be dense for pressure to matter. Across a boundary this large, even extremely thin plasma can influence the shape and behavior of the solar wind. The first major transition is called the termination shock. Before reaching it, the solar wind moves outward faster than the local speed at which pressure disturbances can travel through that plasma. At the termination shock, when the flow slows abruptly, the word shock can sound violent, but this is not a solid collision surface. It is a transition in plasma. Particles change speed. The magnetic field changes. The outward wind becomes slower, hotter in the particle physics sense, and more disturbed. Voyager 1 crossed this region in 2004. Voyager 2 followed in 2007. They did not cross at the same distance from the Sun. That difference was expected. The heliosphere is not a perfectly centered sphere, and its boundaries are not fixed. Solar activity changes the pressure pushing outward. The surrounding interstellar environment is not perfectly uniform. Magnetic fields add another layer of complexity. So the edge moves, it responds. The outer solar system has weather of a kind, although there are no clouds and no air. Beyond the termination shock lies a broad transition region known as the heliosheath. Here, the solar wind continues outward, but it no longer behaves as it did near the planets. It is compressed and redirected as the sun's outward flow meets resistance from the surrounding interstellar medium. For the Voyagers, crossing the heliosheath required years. This alone gives some sense of scale. A boundary that can be drawn as a thin line in a diagram can occupy billions of kilometers in physical space. A spacecraft does not cross the edge of the sun's influence in a moment. It spends years moving through the transition. That is one of the recurring themes of our journey. Nature rarely respects the simple borders we draw on maps. The atmosphere does not stop at a precise altitude. Earth's magnetic environment does not end at a painted line. The solar system does not become interstellar space at a single visible wall. Instead, one set of conditions fades while another grows stronger. Eventually, however, a deeper change arrives. The outward solar wind becomes so weakened that the surrounding interstellar plasma is no longer something encountered at the edge. It becomes the surrounding environment itself. This boundary is called the heliopause. Voyager 1 crossed it in August of 2012. Voyager 2 crossed in November of 2018. Their instruments recorded multiple changes. The population of particles associated with the Sun dropped sharply. Galactic cosmic rays became more abundant. Plasma conditions changed. The spacecraft had entered interstellar space. That phrase needs a little care. They had not left the Sun's gravity. They had not reached another star. They had not traveled into some empty region between solar systems where the Sun suddenly ceased to exist. They had crossed the boundary where the solar wind no longer dominated the surrounding plasma. That is what interstellar space means here. The environment around the spacecraft was now shaped primarily by material between stars, rather than by the Sun's outward wind. The distinction is physical, not philosophical, and yet it changes the character of the journey. For every previous chapter of this outward movement, the Sun was still surrounding the spacecraft in some active way. Its photons provided light. Its wind carried particles past the hull. Its magnetic influence helped shape the radiation environment. Even when sunlight became too weak to serve easily as a power source, the heliosphere remained around the spacecraft like an extended atmosphere of the star. Beyond the heliopause, that atmosphere is behind you. The Sun continues to shine. Its gravity continues. But the plasma touching the spacecraft comes from the space between stars. That space is not empty. The local interstellar medium contains atoms, ions, electrons, magnetic fields, dust grains, and energetic particles. Its density is very low, but it is measurable. Here, temperature becomes a word that can be misleading. Individual particles in the interstellar gas can carry significant kinetic energy corresponding to temperatures of thousands of degrees. Yet, there are so few particles that they would not heat a spacecraft the way hot air heats your skin. Temperature describes the energy of the particles that are present. It does not tell you how many particles are there to transfer that energy, so a spacecraft can move through a gas whose particles are individually energetic, while the vehicle itself must still struggle to preserve internal warmth. This is a reminder that many familiar ideas change, meaning when matter becomes thin enough, pressure becomes tiny, heat transfer becomes weak, distances between particles become large compared with ordinary experience. The environment feels less like a gas and more like isolated encounters, and cosmic radiation changes as well. Inside the heliosphere, the solar wind and the magnetic fields carried with it help modulate the number of galactic cosmic rays reaching the inner solar system. Beyond the heliopause, that modulation is no longer operating around the spacecraft in the same way. Voyager measured an increase in galactic cosmic rays as it crossed outward. The galaxy had become more directly present. There is something almost symmetrical in that transition. Near Earth, the planet's magnetic field shapes the charged particles around us. Farther out, the Sun's magnetic influence shapes a much larger region. Cross both boundaries, and the protective structures associated with home become progressively less important. First the planet, then the star, not absent, just no longer surrounding you in the same way. Voyager 1 and Voyager 2 continue through this environment, carrying instruments built in another era. Their transmitters send weak radio signals back toward Earth. By the time those signals arrive, they have spread across an immense region of space. Large antennas on Earth collect a tiny portion of that energy and recover information from it. The communication delay is now measured in many hours. A command sent outward does not reach the spacecraft until much later. If a response is transmitted back, another long interval follows before Earth receives it. At these distances, mission control is not watching the spacecraft in real time. It is receiving news from the past. The machine may already have experienced another day of interstellar space before engineers finish studying what happened during the previous one. And Still, the sun's gravity reaches much farther. Crossing the heliopause is not the same as leaving the solar system in every possible sense. Far beyond the heliosphere may lie populations of icy bodies bound weakly to the sun, including the distant reservoir, commonly described as the Oort cloud. If that immense structure exists broadly as models predict, its objects would orbit at distances so large that passing stars and the gravitational field of the Milky Way could influence their paths. The sun's physical wind may be gone there. Its light may be faint, but gravity continues to tie distant material to the system. This gives the solar system more than one edge. There is an edge of planetary architecture, an edge of the solar wind, and, much farther away, a less definite gravitational frontier where the sun's ability to hold objects competes with the rest of the galaxy. No single boundary contains all meanings of the word home. The farther outward you travel, the more those meanings separate. Once the heliopause is behind you, the word distance begins to change again. Inside the planetary system, distance was something measured between destinations: Earth to Mars, Mars to Jupiter, Jupiter to Saturn. Beyond the sun's plasma boundary, there are fewer destinations to mark the journey. There is mostly space. Voyager 1 and Voyager 2 are still gravitationally connected to the sun in the broadest sense, but they are moving outward fast enough that they will never return. Their trajectories are open. Each year carries them farther into the local interstellar environment, while the sun gradually becomes another bright point behind them. This is where the scale of the solar system reveals one of its most difficult surprises. The heliopause is far away by every human standard, and yet it is nowhere near the outer limit of the region that may still contain objects gravitationally associated with the sun. Far beyond the planets, astronomers infer the existence of a great reservoir of icy bodies, usually called the Oort cloud. No spacecraft has reached it. No telescope has photographed it as a complete structure. Its existence is inferred largely from the orbits of long-period comets, objects that occasionally fall inward from enormous distances and sweep through the planetary system before returning to the outer dark. The Oort cloud is therefore not known in the same direct way that the Kuiper belt is known. Its overall shape, population, and outer boundary remain uncertain, but the general idea is well supported. During the early history of the solar system, gravitational encounters with the giant planets could scatter icy bodies onto distant orbits. Some would be ejected completely. Others could remain weakly attached to the sun, traveling so far away that passing stars and the gravitation environment of the Milky Way begin to influence their motion. If you could move outward through this region, you would not see a shell of comets. You might travel for immense distances without approaching one. The word cloud describes a statistical populations spread through a volume so large that the individual members may be separated by distances difficult to picture. The sun would remain the center of their long orbits, but it would no longer look like the sun you know. At thousands of astronomical units away, its disk would be far too small for the unaided eye to resolve. It would appear as a very bright star, distinguishable through measurement and familiarity, rather than through any visible solar surface. Sunlight would still arrive. Physics does not provide a point where photons simply stop, but the energy would be reduced enormously. A solar panel designed for use near Earth would receive so little power that it would become almost irrelevant. The practical connection between sunlight and survival would have ended long before. Gravity persists more effectively. That is why a small icy body can remain attached to the sun, even where solar heating contributes almost nothing to its environment. Gravity weakens with distance too, but there is no shielding that blocks it. There is no heliopause for gravity. Instead, the sun's pull gradually becomes comparable to other gravitational influences. A passing star may tug on a distant comet. The combined mass of the Milky Way contributes a weak tidal effect. Over millions of years, these small influences can alter an orbit. A comet that had spent ages far from the planets may begin falling inward. Its journey can take millions of years. For most of that time, almost nothing visibly happens. The sun slowly becomes brighter. Eventually, after crossing immense stretches of cold space, the comet reaches distances where solar heating becomes significant. Frozen material begins to turn into gas. Dust is released. A coma forms. A tail may appear. An object that spent nearly its entire existence in darkness becomes one of the brightest moving objects in the inner sky. Then it leaves again. The cycle is so long that no human observer could watch a complete orbit of many such comets. This is another way the outer solar system changes the meaning of time. Near Earth, spacecraft missions are measured in months or years. Voyager has already forced us to think in decades. In the distant comet reservoir, natural orbital motion asks for millions of years. Human schedules become very small against that background. There is a generational thread hidden inside deep space exploration because no single person has owned the entire story. Engineers who designed Voyager worked with technologies of the 1970s. Some people who later managed the mission were children when the spacecraft launched. Others were not yet born. The machines crossed boundaries that their original designers could model, but could never expect to watch from beginning to end as one continuous human project. Knowledge was handed forward, procedures were handed forward. Old documentation had to be understood by new teams. The spacecraft remained the same physical object while the people listening to it changed. This may become normal for truly distant exploration. A probe built for another star would not merely be a vehicle crossing space. It could become a project crossing generations. And beyond the Oort cloud, even that thought expands. The nearest neighboring star system lies more than 4 light years away. That sounds close when compared with the width of the Milky Way. It is not close to a spacecraft. Voyager 1 moves at a little over 17 kilometers per second relative to the Sun. At that speed, crossing 1 light year would take many thousands of years. Reaching the vicinity of the nearest star would take tens of thousands. Voyager is not traveling toward that star, and it was never designed for such a mission. The comparison simply shows the scale. The distance between stars is fundamentally different from the distance between planets. A planetary system is spacious, but its worlds remain grouped around one star. Interstellar space contains distances large enough that an entire planetary system could be placed inside them many times over without filling the gap. And the farther a spacecraft travels, the more communication becomes an exercise in waiting. A radio signal still moves at light speed. Nothing about the transmitter makes the signal itself slow down, but the delay becomes unavoidable. At 1 light hour, a command needs an hour to arrive. At 1 light day, it needs a day. At 1 light year, the message crosses space for a year before reaching its destination, and a reply requires the same journey in reverse. If a probe were operating 4 light years away, a simple exchange would span more than 8 years. There could be no remote piloting, no rapid diagnosis, no correction based on a situation that had just occurred. By the time Earth received a report, the spacecraft would already be years beyond that moment. The probe would need to interpret its environment, protect itself, make decisions, and continue without expecting immediate guidance. This is the logical continuation of the autonomy that begins much closer to home. Mars requires crews and machines to tolerate minutes. Jupiter requires patience measured in tens of minutes. Neptune requires hours. Interstellar space demands years. Distance does not remove communication. It removes simultaneity. Earth and spacecraft remain connected, but they no longer share the same operational present. There is something useful in imagining a signal crossing that space, not because the signal experiences the journey as we do, but because its path gives scale to emptiness. It leaves an antenna. Earth falls behind. The orbit of the Moon is crossed in a little over a second. Mars' distance scales may take minutes. The outer planets require hours. The heliosphere eventually passes behind. Then, the signal continues through the thin niril between stars. There are no relay towers waiting ahead, no intermediate stations. For months, then years, the radio wave travels through a region where almost every cubic meter contains too little matter for human senses to notice anything at all. At the end, perhaps another machine receives it. What began as electrical activity in one civilization becomes an electromagnetic disturbance crossing interstellar space. That may be one of the simplest ways two distant places can remain connected, not through immediate presence, through information that survives the crossing. The same principle already surrounds you tonight. Much of what astronomy knows about distant objects arrives this way. Although usually through natural light rather than transmitted radio, we see the sun as it was minutes ago. We see nearby stars as they were years ago. We see distant galaxies as they existed long before humans appeared. Astronomy has always been an exchange with the past. Deep space travel simply makes that fact personal. A spacecraft leaving the solar system does not enter a region where Earth has vanished. Earth remains behind it. The sun remains behind it. Their gravity, light, and signals become progressively weaker, but their existence does not depend on being nearby. The traveler has crossed from one environment, and what once felt like a single home has become a small planetary system suspended inside a much larger galaxy. There is one more threshold to cross, and it is not located at any particular distance from the sun. It appears when the journey becomes longer than the systems that support the traveler. Every spacecraft carries clocks of a kind. A battery has a lifetime, a seal has a lifetime. Electronics accumulate damage. Moving parts wear. Radioisotope power sources slowly produce less electricity. Human bodies age. Food reserves are consumed. Medicines lose effectiveness. Materials are exposed to radiation, temperature cycling, and microscopic impacts for years that may eventually become decades. Close to Earth, these limitations can be managed by replacement. Farther away, they must be managed by endurance. And in interstellar space, endurance becomes the mission itself. A spacecraft bound for another star would need to survive conditions unlike those of any voyage humans have attempted. Radiation would continue throughout the journey. There would be no planetary magnetic field surrounding the crew, and no heliosphere providing the same modulation of galactic cosmic rays that exists closer to the sun. Energetic particles would arrive from many directions. Some would interact with shielding, some would pass through it. The problem would not be one dramatic burst, but years of accumulated exposure. Mass helps, water can help, hydrogen-rich materials can help reduce certain kinds of radiation. A habitat could be designed so that sleeping areas and other frequently occupied spaces sit behind stores of water, food, equipment, or dedicated shielding. But every kilogram added to the vehicle must first be accelerated. And acceleration is one of the central difficulties of interstellar travel. The nearest stars are not simply farther versions of Mars or Neptune. They require an entirely different relationship between speed and time. At the velocities reached by present deep space probes, a journey to even the nearest stellar neighborhood would last many thousands of years. To complete such a trip within one human lifetime, a spacecraft would need to move at a significant fraction of the speed of light. That introduces new problems. A dust grain that seems harmless at ordinary spacecraft speeds can carry enormous kinetic energy when the relative velocity becomes high enough. A particle no larger than a grain of sand becomes something the vehicle must take very seriously. Even smaller particles can erode a forward surface through repeated impacts. So the empty space between stars cannot be treated as perfectly empty. A fast interstellar vehicle would need to consider shielding, not only from radiation, but from matter. Perhaps the forward structure would use layers designed to absorb impacts. Perhaps sacrificial material would be placed ahead of the main habitat. Perhaps an unmanned probe could tolerate risks that would be unacceptable for a human crew. Whatever the design, speed turns sparse material into an engineering problem. Then there is energy. Chemical rockets are excellent for lifting spacecraft away from planets and changing trajectories within the solar system. But the energy required for rapid interstellar travel lies on another scale. Concepts proposed over the decades have included nuclear propulsion, fusion-based systems, externally powered sails, and extremely light probes accelerated by powerful lasers from far away. Each approach solves one difficulty by creating others. A sail pushed by light avoids carrying much of its propulsion energy on board, but keeping a beam accurately directed over enormous distances would be difficult. A fusion spacecraft would carry its own energy source, but controlled fusion propulsion at the required scale remains beyond anything humanity has demonstrated. A tiny robotic probe could be accelerated much more easily than a habitat containing people. Shielding, food, water, machinery, and decades of redundancy. This difference matters. Sending information-gathering machines to another star is a difficult problem. Sending human beings is a much larger one. A human spacecraft cannot be reduced to an instrument package. It must carry an environment, pressure, breathable air, water, temperature control, food waste processing, medical capability, protection from radiation, protection from impacts, and enough redundancy to continue after failures that may occur when Earth is years away by radio. The spacecraft would have to perform one of the most difficult transformations in engineering. It would need to stop behaving like a machine assembled from replaceable parts and begin behaving more like an ecosystem. Air would circulate instead of being continuously supplied from outside. Water would be recovered again and again. Carbon dioxide would be processed. Nutrients would move through controlled cycles. Materials might need to be repaired, remanufactured, or repurposed. The distinction between cargo and infrastructure would gradually disappear. A container emptied of food could become raw material. A damaged component might become a source of metal for another repair. Waste would become something to understand rather than simply discard. Deep enough into the journey, there is no away. Everything aboard remains part of the small world traveling between stars. Human beings already practice pieces of this problem. Space stations recycle water. Submarines operate closed systems for long periods. Remote research stations learn to live with limited supplies. Robotic spacecraft diagnose faults and protect themselves without immediate human commands. None of these examples is an interstellar mission, but each contains one part of the logic such a mission would require. Survival depends less on carrying endless supplies and more on maintaining cycles. That is familiar to Earth itself. The water in your body has been through other bodies, oceans, clouds, rivers, soil, and air. Carbon moves between living things and the environment. Nitrogen circulates. Oxygen is produced and consumed. Earth supports life, not because fresh material constantly arrives from somewhere else, but because matter is reused within a planetary system powered largely by sunlight. An interstellar habitat would attempt something much smaller and far less forgiving. A world reduced to rooms, pipes, tanks, plants, machines, and people. If the journey lasted decades, the psychological environment would matter as much as the mechanical one. There would be no changing outside landscape. Stars would shift only gradually. The departure system would diminish behind the spacecraft. The destination star would brighten slowly ahead. Most days would occur in the space between. The mission would need rhythms that make sense without sunrise, seasons, weather, or a natural horizon. Artificial lighting could maintain daily cycles. Work would create structure. Meals would divide time. Private spaces would matter. So would contact with Earth, although every message would become older as the distance increased. At 1 light year away, a voice from home would already describe events at least a year in the past. At 2 light years, 2 years. Eventually a person could receive a message from someone who had changed completely by the time the recording arrived. Children would sound younger. Places might no longer look the same. News would not be news in the ordinary sense. It would be history delivered personally, and messages sent back would enter the same delay. A traveler could describe a birthday, a repair, a scientific observation, or a difficult day, knowing that no response could return for years. Communication would still matter. Perhaps more than ever, but it would no longer remove isolation. It would document the distance. This is where the idea of rescue finally disappears almost completely. Inside low Earth orbit, another spacecraft may be able to bring a crew home. At the Moon, return is measured in days. At Mars, assistance is constrained by orbital mechanics and long transit times. Beyond the outer planets, practical rescue becomes increasingly unrealistic. Between stars, it loses meaning. A second vehicle launched after an emergency would begin behind the first one and face the same enormous crossing. Unless it could travel much faster, it might never catch up. The crew could ask Earth for advice. Earth could send knowledge. What Earth could not send in time would be hands, so every essential capability would have to exist aboard. The doctor would be there. The workshop would be there. The shelter would be there. The spare parts would be there. And when the spare parts were gone, the ability to make new ones would have to be there too. This is perhaps the final subtraction in deep space. Not the loss of light, not the loss of magnetic protection, not even the loss of rapid communication. It is the loss of an external solution. Far enough from Earth, survival can no longer depend on something arriving from somewhere else. The traveling system must contain its own answer. That condition sounds unfamiliar until you look back toward the small planet we left at the beginning. Earth has always lived this way. There is no supply ship bringing oceans, no outside atmosphere waiting in reserve, no second biosphere sent across space when something fails. For billions of years, the planet has carried its materials with it around the sun, cycling them through rock, air, water, and life. A deep space vessel would be far smaller and far more fragile, but the underlying lesson would be similar. Distance eventually turns a vehicle into a world. At the end of this outward journey, there is no final wall. There is only a sequence of environments becoming less familiar. Earth's atmosphere remains behind, then the strongest protection of Earth's magnetic field, then the possibility of immediate conversation, then practical resupply, then abundant sunlight, then the solar wind itself. Each change happens at a different distance, for a different physical reason, and none of them marks a universal border called deep space. That may be the most useful thing to carry back from all of this. Distance is not one problem. It is many problems unfolding together. A spacecraft moving away from Earth does not simply become farther from home. It enters new radiation environments. Its radio messages require more time. Its power systems must adapt to weaker sunlight. Repairs become harder to support. Thermal control changes. Navigation becomes increasingly autonomous. Eventually, the surrounding plasma no longer belongs primarily to the sun. The journey changes because the environment changes. and the machine must change with it. This is why a spacecraft built for low Earth orbit cannot simply be pointed toward another star. The International Space Station is an impressive place to live, but it depends on a nearby planet. Cargo arrives. Crews rotate. Communication is rapid. The station moves within Earth's magnetic environment and remains only hours from the surface under normal return conditions. A lunar spacecraft must do more for itself. A Mars vehicle must do more again. A probe at Neptune must operate for hours without any possibility of immediate correction from Earth. A machine in interstellar space must continue through conditions that no technician can reach. Every step outward transfers responsibility from the environment to the spacecraft. Air becomes a tank and a recycling system. Warmth becomes insulation and electrical power. Navigation becomes software. Protection becomes shielding and trajectory. Repair becomes stored parts, tools, and knowledge. Communication becomes memory carried by light. There is no moment when the laws of physics become hostile. They simply stop providing the conveniences under which human life evolved. The human body expects pressure because pressure has always been here. It expects oxygen because oxygen has always been here. It expects gravity strong enough to shape muscles and bones in familiar ways. It expects radiation levels moderated by atmosphere and magnetic fields. It expects a sun bright enough to define day. These are not universal conditions, they are local conditions. Very local, for almost the entire age of our species. The difference did not matter. The environment of Earth was simply the environment. Only after spacecraft began leaving the ground did we gain the ability to compare it with anything else directly. And that comparison has made the ordinary world look more specific. The atmosphere is not just empty sky, it is mass. The magnetic field is not merely something that turns a compass needle. It shapes the motion of charged particles far above the surface. The sun is not simply a bright object overhead. It powers climates, photosynthesis, solar cells, and much of the energy flow through the planetary system. Even the ability to speak to another person and receive an answer immediately is partly a property of distance. We rarely experience it that way because terrestrial distances are small compared with the speed of light. But across planets, that assumption breaks. Across stars, it disappears. Perhaps future technologies will reduce some of these difficulties. Power systems may improve. Radiation shielding may become more effective. Spacecraft may manufacture more of their own components. Artificial intelligence may help machines respond to situations that cannot wait for Earth. New propulsion methods may shorten journeys that now require decades or millennia. But none of these developments will erase distance itself. Light will still take time to cross space. Radiation will still interact with matter. Heat will still have to be controlled. Materials will still age. A living crew will still require an environment around them. The technologies may change greatly. The physical questions remain. How much energy is available here? What surrounds the spacecraft? How long does a signal need to travel? What happens if something breaks? What can be repaired? What must be carried? How long can the system continue without outside support? Those questions begin only a few hundred kilometers above Earth, and they remain relevant all the way into interstellar space. Voyager 1 and Voyager 2 answer some of them simply by continuing. They are small machines now compared with the distances around them. Their available electrical power has declined over decades. Their instruments have been reduced as engineers preserve what can operate. Their signals reach Earth after crossing billions of kilometers. Nothing dramatic happens during most of that time. The spacecraft moves, the radio travels, particles pass through the detectors, the sun slowly recedes. The galaxy becomes the local environment. That is what deep space often looks like in reality. Not constant spectacle, persistence, a machine doing the next necessary thing in a place where almost nothing changes quickly. One day, the voyagers will stop transmitting, their power will fall too low. A final instrument will become silent. Earth will listen and receive nothing more. But the spacecraft will continue. Their motion does not depend on their radios working. They will travel through the galaxy as inert objects, carrying material shaped on Earth into regions where no object made by humans had ever existed before. Long after their electronics fail, gravity will continue acting on them. Stars will move. The sun will travel around the Milky Way. Spacecraft will pass through changing regions of interstellar gas and dust. They will become less like missions and more like artifacts. And Earth will remain where this journey began. A small world beneath an atmosphere, inside a magnetic field, orbiting a star, whose wind creates a bubble through surrounding interstellar space. From the ground, none of those protections are obvious. You can look upward and see only the sky. But beyond that sky are layers within layers, each extending farther than the last. The atmosphere, the magnetosphere, the region of the planets, the heliosphere, then the material between stars. What changes as you travel outward is not merely how far away Earth becomes. What changes is how much of Earth you have to bring with you. At first, almost none. Then air, then pressure, then radiation protection, then water recycling, then medical independence, then power, then repair capability, then enough autonomy to continue when every message from home describes a world hours, days, or years in the past. Deep space travel is therefore not simply the act of crossing distance. It is the gradual construction of a small environment capable of surviving where Earth's larger one can no longer reach. And, far behind, the blue planet keeps turning inside its shield,